first transistor to be invented and widely used in circuits. There are three doped regions forming two p-n junctions between them, that is NPN and PNP type transistors with emitter, collector and base top. In a transistor, emitter is of heavily doped and moderate. Collector is moderately doped and larger as compared to emitter. Base is very thin and lightly doped. Emitter base junction of the T transistor is forward bias, while the collector base junction of the transistor is reverse bias or vice versa depending on the condition desired. For transistor to be used as an amplifier, the emitter base junction is forward bias and the base collector region is reverse bias. This state is called as active state. Total current entering the emitter current, that is, goes to the base form where most of the current enters the collector and a very small fractions of current leaves the base. Thus, base current is less than collector current. Since the emitter base junction is forward bias, their resistance is lower than the collector base junction, which is reverse bias. We know beta AC is small change in collector current divided by small change in base current. Now at voltage CE is 10 volt, we can read two values of IC from the graph. Then the beta AC is 150. A low input to the transistor gives a high output and a high input gives a low output. The switching circuits are designed in such a way that transistor does not stay in an active state. Output characteristics graph for a transistor gives us the relation between the collector current and emitter voltage. It also gives us the value of base current, but it gives no information about the base emitter voltage. Current amplification factor is the ratio of small change in collector current to the small change in base current, with collector emitter voltage constant. Current gain is ICIB with constant voltage across CE. Transistor consists of two PN junctions in the series of PNP and NPN. Number of depletion layers in a transistor is 2. A transistor made up of two PN diodes connected back to back. Collector is the big component in the transistor. In PNP transistor, majority charge carriers are holes and minority charge carriers are electrons. Transistor is a current driven device since the collector current is called control via base current. In NPN transistor, holes are the majority carriers and free electrons are the majority carriers and holes are the minority carriers. Base current is typically 1 to 5% of the emitter current or collector current for a small signal transistors. Since transistors have a constant current source in the emitter circuit, the input impedance is very high. In common emitter circuit, IE is equal to IC plus IB. IC is equal to IE, therefore ratio of IC upon IE is less than 1 always, so alpha is less than unity, its value lies between 0.9 to 0.995. The most commonly used transistor arrangement is common emitter arrangement. In BJT, base region is sandwiched between emitter and collector. BJT operates in active region to work as amplifier and oscillators. In transistor, base is very lightly doped as compared to the emitter because by doing so, IB is high, recombination is decreased in the base region. The input signal is applied between the base and emitter terminals. Input current flowing is the IB, and hence characteristics are represented by the plot between VB and IB. If the collector base junction is reversed bias and the base emitter junction is forward bias, then the BJT functions in the active region of the output characteristics. If collector base junction and the emitter base emitter junction are both forward biased, then the BJT functions in the saturation region of the output characteristics. If the collector base junction and the base emitter junction are both reversed biased, then the BJT functions in the cutoff region of the output characteristics. The transistor in which one N-type material is topped with two type 2p-type material. Such type of transistor is known as PNP transistor. Base will be of N-type material. In transistor, one N-type material topped with two p-type materials in PNP transistors. In common base amplifier, input signal is applied to at emitter terminal while the amplified output signal is obtained at the collector terminal with respect to ground. For AC signals, the base terminals is specifically connected to ground through the capacitor. Even output resistance is very high and hence the current gain is approximately equal to unity. Due to this, there is no possibility of current amplification. Consequently, the CB amplifier exhibits high voltage gain. In common collector configuration, also known as emitter follower, because the emitter voltage follows that of the base, offering a high input impedance and a low output impedance. It is extensively used as a buffer. The voltage gain is unity even though the current gain is high, the input and output signals are in phase. In common base configuration, input impedance is low while the output impedance is high. Although voltage is high, the current gain is low and overall power gain is also low when compared to the other transistor configuration available. Thus, there is no current amplification because of unity current gain. In cutoff region, both the junctions are reversed bias. The transistor has practically zero current because the emitter does not emit charge carriers to the base. There is negligibility current due to minority carriers. In this mode, transistor act as an open switch. In saturated region mode, both the junctions are forward biased. The negative terminal of the battery is connected to the emitter. Collector current becomes independent of base current. In this mode, the transistor acts as a closed switch. Depending on the type of load, a collector current is induced that would turn on the motor or LED. The transistor in the circuit is switched between cutoff and saturation. The load, for example, can be a motor or a light emitting diode or any other electrical device. Output devices like LEDs only require a few milliampere at logic level DC voltages and can therefore be driven directly by the output of a logic gate. However, high power devices such as motors or lamps require more power than that supplied by an ordinary logic gate. So transistor switches are used. Therefore, LED is driven by transistor logics. From the cutoff characteristics, base emitter voltage in a cutoff region is less than zero point 0.7 voltage. The cutoff region can be considered as a off mode. Here, VB is greater than zero point 0.7 and IC is equal to 0. Here, transistor will be biased so that maximum amount of IB is applied, resulting in maximum IC, resulting in minimum emitter voltage drop, which results in depletion layer as small as possible and maximum current flows through the transistor, therefore decreases by decreasing emitter voltage drop. From the saturation mode characteristics, the transistor acts as a single pole, single throw, solid state switch. A zero IC flows with a positive signal applied to the base of a transistor. It turns on like a closed circuit switch. Therefore, VB in saturated region cannot be predicted. Sometimes DC current gain of a BGT is too low to directly switch the load current or voltage, so multiple switching transistor is used. The load is connected to ground and the transistor switches power to it. The switching power with PNP transistor is sourcing current and NPN transistor is sinking current. BGT have three semiconductor region, regions: emitter, base, and collector regions, and operates at defined region of cutoff mode, active mode, and saturated modes. A BGT operates as an amplifier in active mode and as a switch in cutoff or saturation mode. In cutoff mode, there is no current flowing through the BGT. Hence, both junctions, that is B and EC, must be reversed biased. Else, if there either of them is forward bias, then the current will flow. Collector current depends linearly of saturation current and exponentially to the ratio of voltage difference between the base and collector and thermal voltage. In physical mode of a common base transistor amplifier, the input is measured at the emitter terminals of the BJT biased device, whereas output is measured across the collector terminal of it. To determine the input characteristics, the collector base voltage is kept constant at 0 volts and the emitter base voltage is increased from 0 volts to different voltage levels. For each voltage level of the input voltage, the input current is recorded. And to determine the output characteristics, the emitter current is kept constant at 0 amperes and the collector base voltage is increased from 0 volts to different voltage levels. For each voltage levels of the output voltage, the collector current is recorded. Dynamic input resistance, that is RI, is the ratio of small change in base emitter voltage to small change in emitter current, with collector voltage keeping constant. Here IC is equal to beta into IB. When no voltage is provided at the base, then no current passes from emitter to collector. So, even if very high potential difference is applied to the emitter current collector junction, no current flows through it. This configuration is used for switching in various appliances using BGT. BC547B, that is BGT, most common and widely used NPN transistor. It is small, cheap, uses less power, and fulfills most of the requirement for general purpose use. In BGT, both electrons and holes are responsible for conduction. The term bipolar itself means two polarities, which represents that both charged particles are responsible for the conduction in the BGT. A BGT has two PN junctions. First PN junction between the base emitter terminal and second PN junction is between base collector terminals. A base is always between emitter and collector. Point 0.7 is the minimum voltage required to make the base emitter junction of a real silicon BGT in forward bias. This zero point 0.7 volt potential difference between base and emitter terminals takes the PN junction in forward bias. Collector to emitter voltage and collector current are the parameters considering which transfer characteristic curve of a BGT is made. It is voltage versus current graph in which current lies on y-axis and voltage on x-axis. IC is equal to beta into IB. FET, field effect transistors, are voltage control devices. By applying some voltage between the gate and source, the drain current can be controlled. In order to control the operation of FET, the gate and drain voltage is varied to operate the FET in different regions of operations. Because of the silicon dioxide insulator topped between drain and source at the top, the resistance offered by this is very high. The insulator will stop the flow of current from the one part to another, which acts as an open circuit. BGT is usually built with a thickness of up to 1 cm, whereas FET uses a fabrication technique which makes its size in mm. Therefore, BGT larger than FET. Because of its small size, the IC chips can be made even smaller, which reduces the wear and tear. The process technology used with constant at which the ratio of width and length the FETs is made more advantageous. For FET, the current reaches maximum, that is IDSS, occurs when VGS is equal to 0 volt and VDS is greater than pinch off voltage, that is VP. When the gate to source voltage is less than pinch off, both the junctions will be reversed bias and hence no current flows. So from the equation of ID, if VP is equal to VGS, then ID will be 0 ampere. by varying the gate to source voltage. Resistance can be varied as follows: RD is equal to R0 upon 1 minus V2GS upon Vp. Therefore, FATE as voltage controlled resistor in ohmic reason. When a voltage greater than pinch off is applied, the current starts flowing from drain to source for N channel FET, and for P channel FET vice versa, that is source to drain. A forward bias drain and gate is the reason for the flow of electron from drain to source. As a conventional current flows opposite to the electron flow, the current will flow from source to drain in p-type channel FET. FET are unipolar transistors as they involve single carrier type operation. FET's conductivity is regulated by the voltage applied to a terminal, that is gate, which is insulated from the device. In FET, the current enters the channel through source and current leaves the junction through drain. Other than the three terminals, source, drain, and gate, there is a fourth terminal called as a body or base. This is used to bias the transistor in operation. In FET, the width is greater than the length of the gate. Length gives the distance between source and drain. Width is the extension of the transistor in the direction of particular to cross sections. Gate permits the electron to flow through or block their passage by creating or eliminating the channel between source and drain. Gate permits in N-channel depletion mode device, as the depletion region width expands, it encroaches the channel from the sides and the channel becomes narrow. A positive gate to source voltage increases the channel size and allows the electron to flow easily. Saturation mode, which is in between the ohmic and saturation region, is used when amplification is needed. The FET physical structure, which contains silicon dioxide, provides infinite resistance, hence no current will flow through the gate terminals, therefore IC is equal to 0 ampere. For an FET, same current flows through the gate and source terminal, hence IS is equal to 1 milliampere. Here, VDS is equal to VDD minus ID into RD. Therefore, RD is equal to 2 kilo ohms. FET monopolar devices with only one carrier type, either electron or holes, providing current flow through the device and channel. FETs employs electrons, while the p-type channel FETs employs holes as a source of current. The current flows in the device is due to the majority carriers. In an n-type JFET, it is due to the electrons, and in a p-type JFET, it is due to holes. The pinch-off voltage for an n-channel JFET is negative, that is not greater than 0. The depletion region would extend to the n-channel if the reverse bias in the gate to source voltage increases, which means the gate to source voltage has to be negative since the gate is n-type. An n-channel is always on depletion mode JFET, since the channel for current flow from source to drain is always present. This is in contrast to P channel JFET, which needs to be provided with a channel for the flow of current. A JFET has three terminals, namely source, gate, and drain. Source Gate source PN junction is always reversed bias because it is forward, then all the channel current will flow to the gate, not to the source, ultimately damaging the JFET. A common base configuration of a PNP transistor is analogous to common gate configuration of a JFET. When drain voltage is equal to the pinch-off voltage, the depletion layers almost touch each other. IDSS is referred to as the drain current for zero bias because the gate source voltage requires no bias voltage to operate. The gate source voltage is just zero. No voltage needs to be applied to it. Therefore, IDSS is to drain to source current with gate shorted. A JFET has high input impedance because input is reversed bias. JFET is properly biased condition acts as an voltage controlled current source. The input resistance of a FET is typically very high in order of mega ohms, near about 100 mega ohms. FET is a voltage driven and control device, that is, output current is controlled by the electric field applied, and it is three terminal device. Unlike